Well, good morning, evening, or afternoon. It's good to see you all accessing the information that we're providing to you, and we just want you to keep working on things in a timely manner and reaching out with any questions during the day or during your teacher's office hours. Today, we're going to move into looking at Avogadro's law. We're going to kind of recap what STP means, and we'll start looking at what we call the ideal gas law. And there's three different versions. We're going to focus on version 1 today. Before you move through these set of notes here, we just want you to make sure that you go back and please complete the gas law recap, which should be in your day 6 folder. That's going to help you review a little bit. It'll help you with just some of the terminology that we'll be using again today. And that's kind of like your big takeaway from last week. So please go back and work on that before continuing through. We're going to start today looking at what we call Avogadro's law. And Avogadro is somebody that you should recognize that name. And we can relate it to gas as well. So if we take a look at 3 different samples of gas here, we've got hydrogen, oxygen, and carbon dioxide. If we set those to equal volume at the same temperature and pressure, then they would have the same number of molecules as well. And you'll see that word molecules, and that's something that we did associate with Avogadro's number. So again, our 3 balloons that we have up here, the hydrogen, oxygen, carbon dioxide, are all the same volume. And we're going to treat them at the same temperature and pressure. So if we ask the question, if all 3 balloons are at the same temperature and pressure and the hydrogen balloon has 2 moles of atoms in it, how many atoms are in the other 2? So again, the big thing here is same temperature and pressure. So if we have the O2 balloon is 2 moles of atoms, and the CO2 balloon has the 2 moles of atoms. Oh, my apologies for that. Because they're the same temperature and pressure, they're going to have the same amount of atoms. So it's really neat the way that plays together, and it's kind of cool to see Avogadro coming back around and working back into some of our gas laws. With that being said, there's going to be a time where we may bring back Avogadro's number into gas laws. Taking a look then at, sorry, let me flip my notes page here. We're going to bring back in this idea of STP. And STP, if you recall from the little recap quiz that you hopefully just took before this, STP stands for standard temperature and pressure. We have a standard temperature of 273 degrees Kelvin and a standard pressure of 1.00 atmospheres. So if the problem states STP, we are going to be able to use this new conversion factor. 1 mole of any gas occupies 22.4 liters. But again, I want to emphasize that it has to be at STP. So we're going to be able to write out some conversion factors, and this formatting here should look familiar to you. And we'll use dimensional analysis to cancel out units along with that. So let's take a look here. Again, if all of these gases above are at STP, how many moles of each gas would be present? We do want to provide to you a reminder that your 7 diatomics, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. If you look at your periodic table, again, it creates that 7 with all of those diatomics. So please don't forget that. We are dealing with gases, so we'll be seeing those quite a bit. But we can set up some unit cancellation here. We'll start with nitrogen, 44.8 liters, and that's our given over 1. And we're going to use our conversion factor. The first conversion factor here is has the liters on the bottom so that we can cancel out liters and we can convert to moles. And once you plug that in your calculator, you would come out to 2.000. We're going to go back to our initial, right, our given 44.8 to determine sig figs, and we'll put that in scientific notation as well. We're going to continue to use scientific notation as we move throughout this content. So as a reminder, please get in the habit of doing that. We'll go ahead and do carbon dioxide as well at 11.2 liters. Again, same cancellation because we need to cancel liters. And we would get 0.500. And then, of course, we'll translate that into scientific notation as well. As a reminder, with this being a video, you can pause, you can rewind, take a look at another scenario. Again, also as a reminder, these are STP, and if we notice that the volume decreases from nitrogen down to carbon dioxide, our number of moles decreases as well. So you'll want to make sure that your math lines up with your logic. It's always good to kind of think of the big picture. So if we're decreasing volume at STP, our moles should get smaller. That way you can check your final answer. And if your final answer ends up getting larger, then maybe you flipped your conversion in the middle. So something that will help you out. On the next slide, if both O2 and Cl2 gas containers each have 44.8 liters, which has a greater mass inside. So as we introduce mass is where things begin to change, because as we take a look at the actual identity of the gas, they're going to be different due to the fact that they have different mass on the periodic table. So use the periodic table to determine the molar mass and to determine, the molar mass of oxygen and the molar mass of chlorine. And with those being diatomics, make sure that you are taking those masses on the periodic table to the 100th place, 16.00 for oxygen, but again, oxygen's diatomic, so we would multiply that by 2 to end up with a total of 32.00, and the unit for molar mass, as a reminder, is going to be your grams per mole of O2. And then for chlorine, 35.45 on the periodic table times 2, 70.90. So again, molar mass, the big thing here is just making sure that you keep in mind that those diatomics. So example problem here, kind of tying it all together. You see at STP. Because you see at STP, that allows us to use our 1 mole is equal to 22.4 liters. So at STP, calculate the volume of 7.08 moles of nitrogen gas. And so as the usual, we'll put our given over 1. If I can get this decimal point, there we go. 0.08 moles of nitrogen gas. And then we're going to use that conversion factor to cancel our units. As a reminder, it's always helpful to maybe write your units first. I know I'm going to want to cancel moles to be left with just liters, and then we can pick the correct conversion factor based off of that information, which would be 1 mole of N2 on the bottom and our 22.4 liters on top. I want to continue to remind you that it's because we're at standard temperature and pressure is what allows us to use the 1 mole equals 22.4 liters. If we are not at STP, we are going to end up having to use a different calculation that involves something that we'll see here in just a moment. So again, please make sure you're typing these into your calculator. It'll come out to 158.5. And as we go back to our given, which was the 7.08, we know that we are going to need only 3 significant figures, which would come out to 159. And then we put that in scientific notation, 1.59 times 10 to the second liters of N2. So there's a couple things that we want to remind you is that this number out in front, that would be your digit term, and then the 2 is the exponent on the times 10. So that'll come into play as you're working through the Polaris assignment. So here's the student example. You've got the answer is in parentheses. If you're having trouble coming up with that answer, and you could check your work on the teacher filled in version. The first style then, we're going to look at for ideal gas law. There's 3 different versions of ideal gas law. The first one is the equation PV equals nRT, and there's a couple things that we need to know about all of the equations that we use for ideal gas law, and that is the pressure needs to be in atmospheres, your volume needs to be in liters, N is going to be a somewhat new symbol, and that's going to be moles, and your temperature needs to be in Kelvin. Before, when we were working with the other gas laws, we said that, hey, you can leave your volume in milliliters if you'd like. Well, that no longer applies here. You have to be in liters. And the reason why is because we have this new constant. The constant has the variable R, and that constant is called the gas law constant. And basically, it's a ratio. It allows you to relate pressure, volume, number of moles, and temperature for different samples of a gas. So these are going to be, for the most part, mathematical calculations where you're solving for the unknown. The big thing is just to make sure that you are in the correct units for each particular problem. So if we take a look here, we're going to use guess method. And our G, we're going to start detailing our givens. We've got 0.500 moles. And we have a volume of 10.0 liters. We've got a temperature of 25.0 degrees C. Again, have to be in Kelvin. You don't need to show this calculation, but again, I'm going to put it on here as a reminder that you must convert your temperature to Kelvin. And then that R value is a constant. It is on the back of your periodic table under the constant section, so you can always reference that if you're working out some of these problems and you don't have this document open. And our unknown for this, it's asking us to solve for pressure. Now, our pressure is going to come out in atmospheres, and the reason why is because if we look at our unit for the R value, you're going to see that the pressure there is atmospheres. So whatever you're solving for, the unit's going to come out to whatever is in that R constant value. My equation is going to be PV equals nRT. And again, I want to emphasize now is the time for you to double check that all your units are in the correct format, because the easiest way to miss a problem here is to plug in a temperature in Celsius or something along those lines. If we go ahead and manipulate our equation, we're solving for pressure, so we're going to need to divide both sides of the equation by volume. To get pressure is nRT over V. And at this point, we can begin plugging in some numbers. And we're going to have 0. We're going to plug in our number of moles here. So 0.5 times that. I'm going to switch to a different writing style here. 0.500, and we're going to have that R constant in there as well. and the temperature divided by that volume. Plug everything in our calculator, comes out to 1.223. Please make sure you are pausing the video after you get everything written down. I know I don't leave a lot of time in between getting the equation written and writing typing in the calculator, but please make sure you do that. And so after we go back to our givens, our least number of significant figures on our given is 3. So that's going to round to 1.22 times 10 to the 0. And that's going to be a pressure of atmospheres. So again, atmospheres would be your unit. P would be the variable that you're solving for. 1.22 would be your digit term. And 0 would be the exponent. So just a quick reminder there. Let's see here. You've got a student example then on the next page. So please go through. Here's the answer. If you need some help with what goes where, you can check on the filled in version. 0.90 degrees Celsius. Don't forget to convert that to Kelvin. And then you're going to use that PV equals nRT to solve for that unknown volume. Notice that it's going to tell you to spit out the volume in milliliters. You're going to solve for it in liters, and then you're going to have to do a conversion to get to milliliters. So please go in then, work on the Polaris assignment for Ideal Gas Law version 1. You'll see it in the correct folder. Your highest score will work. Feel free to work together on that. And if you're seeking additional help, please move into the Ideal Gas Law worksheet. This is not something that's mandatory. Answers will be given, and then consider completing additional problems and discussing them with peers or asking questions with the teacher before the final homework quiz on that. So thank you very much. Reach out to your teacher if you have any questions.